Okay, I've been mostly following the book and skipping only whole sections if I thought I could afford to skip them. But for 6A and 6B, I'll skip a lot of things in there because for me the only interesting part is Graham-Schmidt. So this will be really a cursory review of these things. Cursory review of 6A and 6B. And it starts with the dot product that you learned in vector calculus. So do you remember how to do a dot product? If you have like A, B, C dot with D, E, F, what's the dot product?
AD plus B.
AD plus BE plus CF, right? And this dot product has, so if I call this V1 and call this as V2, then this dot product has several properties. And let's use V1, V2 as a symbol for dot product. Then we have the following thing. So this is bilinear. Okay. So what does bilinear mean? It means that if you have AU plus BV comma W, that's A times UW plus B times VW. See how this is same as this, like the addition splits and constants can be brought outside. So that's exactly the same as saying that if you fix the second vector and you think of it as a function of the first vector, then it's a linear function. Does that make sense? Okay. And same thing happens for the other case as well. If you have U, comma AV plus BW, so that you're fixing the U, then first of all, addition splits. And then any constant can be brought outside. So it's like A times UV plus B times UW. And that's what it means to be bilinear. And B, this is positive. What that means is that if you put the same thing, that's non-negative. Okay. Now, why do we say that's positive whereas the inequality really says non-negative? That's because there's this third property, which is this is definite. That's saying that if VV is actually equal to 0, that only happens if your vector is 0. Okay? And these two properties together is called positive definite. So, as a summary, we can make the following statement: is that dot product is bilinear positive definite form. And once you have this idea, then you want to extend this to any vector space. Note that on Rn is different from the usual vector space in the sense that this has a natural, it has a canonical basis, right? Canonical means natural. So there's a choice of bases that's quite natural in Rn. What are those? Those are E1, E2, E3, the standard unit vectors, right? So over those standard unit vectors, we define dot product like that, but in a generic vector space V, we don't have that luxury, right? This one doesn't have a standard unit vector, so what can you do? You can only, if you want to talk about inner product, you can't have a formula like this because, like, what do you mean by ABC? ABC really means A times E1 plus B times E2 plus C times E3, right? But E1, E2, E3, the standard unit vectors don't exist on generic V. So we're not allowed to write this formula down. And therefore, instead of giving an explicit formula, what you have to do is you have to work with an abstract condition about the formula, which is that we want something that's bilinear and positive definite. Okay? Now, so that's something to think about. There are two more properties that are pretty important that you learn in the dot product, which is that, first of all, there was something called the norm, which is like the size of a vector, and this was a relationship, right? Where this V was, if V is equal to ABC, A comma B comma C, this was square root of A squared plus B squared plus C squared, right? So that was the norm. But did you notice that when we were talking about the vector space so far, we've never talked about the size of a vector? We never did. Okay. So far, when we are talking about vector spaces, there was no size, and therefore, what we are going to do from now on is that this will be thought as the definition. So we're going to say norm of V by definition is defined as the square root of this. Okay, so if you have an inner product, let's say you have an inner product space, meaning that it's a vector space equipped with certain formula. There's a function that takes in two vectors and gives you a number with these properties. And if that's given, then we define the norm of a vector in this way. Okay? So that's one thing that we're going to do. Another thing that we're going to do is when dot product of two vectors gave us 0, what did we say? We said,
Orthogonal?
Huh?
They're orthogonal?
Yeah, they're orthogonal. Right? So we say if the inner product of two things, dot product of two things are 0, we say U and V are orthogonal, right? And that idea will be also carried over to a generic vector space equipped with some dot inner product. So from now on, in chapter 6a and afterwards, when we're given a vector space and say this is a vector space with an inner product, the way we are going to think about it is that it's some generic vector space. It doesn't come with the the standard unit vectors ever. We don't know them. But we're given some mysterious inner product. That mysterious inner product will have these three properties, and it's going to allow us to talk about measurement of a vector, size of a vector, and it will also allow us to talk about two vectors being orthogonal. Okay? So that's the idea. All right. Okay, so this is what I said so far, but this is slightly wrong because this is in the case when the base field is real. Okay. When it comes to complex, you have to be careful because for complex numbers, you can't talk about bigger than 0, right? So you might think, well, how does this make any sense for complex when the base field is complex? And the idea is this. So there is something called the Hermitian inner product. Hermitian inner product on Cn. And the standard Hermitian inner product on Cn is, it's almost this, except that for the second part, you need the bars. Okay. Now, what's the purpose of that? Well, let me just do a quick calculation over here. Suppose you have let's think about C2, okay, C2. So what's a vector in C2? A plus bi, C plus di, right? Now let's think about what happens if we did an inner product of A plus bi plus comma C plus di with itself. A plus bi, C plus di. Because I want to show you what happens about this condition, right? So let's see what happens. Well, the definition is it's this times this, except the second one you have to do the complex conjugate. So you have to do A plus bi times the complex conjugate of A plus bi plus C plus di times the complex conjugate of C plus di. But what is the complex conjugate of A plus bi? This is A minus bi, right? So it's A minus bi, and then plus C plus di times C minus di. Okay? What does this give you if you FOIL them out? Well, it's A plus b times A minus b, right? It's a difference of two squares. So it's A squared minus bi squared, but I squared is -1, so you end up with A squared plus b squared. Same thing here. It's going to end up with C squared plus D squared. Oh, look. A, B, C, D themselves are real numbers, right? Although A plus bi was a complex number, A and B and C and D, these are real numbers. So when you see this, this is definitely non-negative. And the only time that this is going to be equal to 0 is when every one of these A, B, C, D are 0. Okay? So the reason that you want to put a bar over here is so that you can still talk about positive and definite. Okay? You can only talk about positive and definite when you have the bars, the complex conjugates in the second part. Okay? So these two are still preserved. However, that causes a bit of a problem when you talk about bilinear, because if you have any coefficient multiplied to second vector, that becomes conjugated, right? So what happens is that it's linear on the first component, first argument. It's linear in the first argument, but in the second argument, it's no longer linear. It splits. The addition splits. That doesn't change. But when the coefficients comes out, they come out as conjugates. Okay? So, therefore, this is sadly no longer true. And in fact, you can't have everything. So what you end up saying is there's a special word for this kind of form. And when I say form, I'm really saying it's a function that takes in two vectors and gives you an element in F. Okay, so this thing is it's a map from V cross V to the base field F. Okay, so so you have a form which is not bilinear. It's something called sesquilinear. Okay, and therefore you can say, so in general, an inner product on V is a positive definite sesquilinear form. Okay? There's something in my eyes. Sorry. Okay. All right. Okay, so you have once you have an inner product that's like this, and by the way, when your base field F is just a real field, then sesquilinear just becomes bilinear, right? But because we can sometimes work on C, we have the sesquilinear. But as long as you have such an inner product, you can still talk about size of the vector, and you can still talk about being orthogonal, right? Okay, so an orthonormal basis, often abbreviated as ONB, is a basis V1 through Vn for a given vector space V with some equipped inner product, so that Vi, Vk is 1 if I and k are equal, and 0 if I and k are different. And the ortho part comes from the 0, meaning that if you have two different vectors, their inner product is 0, and as we said before, if the inner product is 0, that means they're orthogonal. Okay? So if you just have this, then it's just an orthogonal basis. But normal part means it comes from normalization. What's a normalization of a vector? You have arbitrary size vector. You can shrink it so that it has size 1, right? So this condition really says that Vi is 1, but that's by definition norm of Vi squared, right? And because this is a positive number, that means the norm of Vi is 1. So this part is saying that the vectors are normalized. Right? Okay, so that's the definition of an orthonormal basis. And you want to have an orthonormal basis because it makes finding the representation of any vector very easy. So suppose V1 through Vn is an ONB, orthonormal basis. Okay? Then, for any V in V, we have V equals to V, V1, V1 plus da da da, V, Vn, Vn. Okay. Let's show this proof. Well, first, because the list given to us is a basis, V must be equal to some A1 times V1 plus A2 times V2 da 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 AN times Vn. Right? That we've been talking about this the entire semester, that if you have a basis, you can represent vector as a linear combination uniquely. But now, think about what happens if you do V and then V1. Well, then you have A1 V1 plus da 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 AN Vn with V1. So I'm just replacing this V by the right side. And then we use the property that the inner product is sesquilinear. Sesquilinear means that it's linear in the first component, first argument. So that's going to be same as A1 V1 V1, A2 V2 V1, da da da, AN Vn V1. Okay. What is V2 inner product V1? If you have two different vectors in an orthonormal basis, they are
0.
orthogonal, so 0. Okay, so 0, 0, every one of them will be 0 except this guy when you have V1 and V1. Okay, if you have V1 and V1, what's that? 1, right? So you end up with A1 times 1. Oh, so that means A1 is equal to V times V and V1 inner product. Inner product of V and V1. Okay. Now, if you did this same thing for A2, if I replace V1 by V2, that's going to pick up A2, right? And so on, so on. So in general, you keep going, you end up saying that all the coefficients AK is really V and VK. So now once you show that, then you can replace all the coefficients, and this is the formula that you get. Right. Now moreover, you can see that the norm of V is equal to, well, this is square root, by definition, it's the square root of VV. But if you use this idea, then you can see that this is same as square root of, it's VV1 squared plus da 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 VVN squared. So in other words, this is, if A1 is the coefficient of V1, A2 is the coefficient of V2, this is like A1 squared plus da 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 AN squared. That's what I'm saying. Okay. So that's another thing that you can easily prove. So let me skip that part. And now we arrive at an important theorem or important procedure called the Schmidt procedure. here, let V1 through Vn be any basis of V. Then define U1 as V1 divided by the norm of V1. You've seen this before, right? This one is called normalization. So what's the size of U1? If you divide any vector by its size, let's say this vector has size 2, and you divide it by 2, now what's the size of this vector? 1. It will always give you 1, so that becomes a unit vector automatically. But now what we're going to do is we're going to say U2 is you take V2, subtract the component of V2 that's in the direction of U1, and you do a subtraction, okay? So this portion is what's known as the orthogonal projection, okay? So the idea is if you have V1 and then V2, what you do is you take V2 and here's V1, and what you do is you take the plane that's orthogonal to V1. So this is like it's hard to draw 3 dimensions, but this is orthogonal, and what you do is you project this to that orthogonal plane of this vector, okay? So that this resulting vector will be orthogonal to the original one. Okay? So this is going to give you an orthogonal vector, and since we're not even starting the proof, I shouldn't be doing this, but just quickly, let's see what happens if I do U1 inner product U2. Well, by definition, this is going to be U1 V2 minus V2 comma U1 U1. Okay. And then you have U1 V2 minus U1 V2 U1 U1. Oh, there's something that I forgot to say. Sesquilinear means that if you have UV, the same as VU with the bar. Okay. So the way we define the Hermitian, you can see that this is also true. Okay. So I forgot the name from the textbook. What does the textbook say? This property is what? Anyone looking at the textbook? What is the property? Huh?
Conjugate symmetry.
Conjugate symmetry. Thank you. Yeah. So if you switch these two around, you get the complex conjugate, and that's called complex conjugate symmetry. And then I have to talk about that because this is a number that's in the second component. When you bring this out, you end up with a conjugate. You get the conjugate, and then it's still U1, U1. But then, as I said, this is the same as this flipped without the conjugate. So these are exactly the same, but what is U1 inner product U1? It's we made it a unit vector, right? So this has size 1. So that means this is size 1, therefore this is just 1. So it's equal to 0. And what does that show? That means that these two are orthogonal. All right? So I just wanted to show you that part. And later on, when we actually prove it, we'll be doing the same thing, okay? But if I just stop here, then it won't be a unit vector, so you still have to make it a unit vector by doing this. You divide it by this guy. Okay? Now, whenever you divide by something, you should always be worried about, like, what if the denominator is 0? In this case, it's never 0 because v1 and v2 are linearly independent. Being a basis means that these two vectors are linearly independent, so u1 and v2 are linearly independent. And since these two are linearly independent, there's no way that this could be 0. Okay, so now take a guess. What would be the definition of u3? u3 would be v3, but now you have to get rid of all the components in the direction of u1 and u2. So you get rid of those directions so that you end up with only the orthogonal part, and then you normalize it. Okay, so that's the idea. Okay, so what should I subtract? v3 u1 u1. Okay. All right, minus. Let's see if you can guess what the next one is. What should I put over here? Now this time I have to get rid of the component of v3 that's in the direction of u2. So how do I project over u2? v3 u2. Okay. So yeah, if you have a v and then if u is a unit vector, you learned that this is what's known as the component of v over u. Okay, and then if u is a unit vector, this one is known as the projection of v onto u. Okay. And then if you have v minus v u u, that's known as the projection perpendicular u. So these are some of the things that you learned in vector calculus. Not many books do this one, so maybe it's likely that you only saw the first two. Okay. But that's what we're doing. We're just taking the components of the third vector and deleting the. We're taking the third vector and deleting the components in the direction of u1 and u2. And once you get rid of them, you normalize it by dividing. Okay. So you just keep going. Okay? So in general, what you do is un is going to be taking away from vn the component of vn u1 minus da 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 all the way up to minus vn with un minus 1 un minus 1 divided by norm of. I'm just going to put a dot here to say that you're just doing the same thing. You're normalizing. And the statement is that then u1 through un is an ONB, orthonormal basis. Okay. So let's show this by induction, where the very first case is so proof. these are all already normalized, the only thing that we have to show is that if ui and uj are different, then they're orthogonal. Okay? So we prove by induction. Say u1 through uk are orthogonal for or mutually orthogonal. Okay, mutually. So you take any two vectors. If you take the inner product as 0, let's say that. Okay. Then if I do, then uk plus 1, by definition, is this one where it's vk plus 1 minus vk plus 1 u1 minus vk plus 1 uk, and then u divided by something. Now, because we're just trying to show being orthogonal, this denominator is not going to do anything. So we just need to show that the numerator is orthogonal to every one of these. Okay. So suppose you have uj, and then let's do uk plus 1 and uj. And I want to show that this is 0. Okay. So j is anything between 1 through k, and we want to show that this is 0. Okay, well this is like, if I talk about this number, let's just talk about this number as some k, capital K. Okay, so in that case, so if we define the denominator as k, then you get 1 over k, and then vk plus 1 minus vk plus 1 u1 da 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 minus vk plus 1 uk, and then uj. Oh, that's what you get. And then 1 over k, well, by using linearity on the first component, you can now write this as vk plus 1 uj minus vk plus 1 u1 uj minus da 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 minus vk plus 1 uk uj. And then these coefficients all come outside, right? And if you look at what you have, we know that it's mutually orthogonal. So u1 and uj, as long as j is not 1, this inner product is going to give you 0. So all of these will be 0. Sorry, there should be uk here. So uk, uj will also be 0 if j is not equal to k. So the only thing that's not 0 will be when you have uj. So it's going to be 1 over k, vk plus 1 uj, minus vk plus 1 uj. So this is the only thing that won't be 0. Okay. But furthermore, if I move this outside, then you get uj. But what is uj, inner product uj? It's 1, right? So you end up with 1 over k, vk plus 1 uj, minus vk plus 1 uj times 1, and that's equal to 0. Done. Okay? Consider example problem. Consider P2C, which is like ax squared plus bx plus c with a, b, c, and c. Equipped with inner product apply Graham-Schmidt procedure to 1x squared to obtain an orthonormal basis. Okay, so I skipped a lot in the textbook, so in the textbook it does explain why this will give you an inner product. But for any function, you can integrate it over any interval. With the second part, you put a conjugate. That gives you an inner product. Okay. And in fact, this is somewhat a natural kind of inner product for function spaces. So later on, when you take real analysis and learn about L2 spaces, the inner product in L2 spaces, if you have an L2 space over the interval 0 to 1, open or closed, in that case, the inner product defined on two functions over here is exactly this one. Okay. And slightly more generic form of inner product that you get to use on solving PDEs when you do Sturm-Liouville, it's a to b of f of x times gx bar with some weight function. And the weight function is usually real in order to have positive definite. Okay. So that's again an inner product, right? So the weight function has to be positive over the interval, or at least non-negative over the interval. Okay, so this is you can check that this is indeed an inner product. It's sesquilinear and positive definite. And the idea is to apply Graham-Schmidt to this to obtain OND. So let me show you how this is done. So solution. First, we have to think about the norm of 1, which is the square root of 1 inner product 1, which is square root of, well, here I gave you 0 to 1, but sometimes this could be 0 to 2 or 0 to 3 or negative 1 to 1. It could be anything, right? So you have to be careful. Here I'm doing 0 to 1 because that's what's given. Is 1 times 1 bar. Conjugate of 1 is this 1, so there's nothing going on here. So this is just conjugate of 1 is 1, 1 times 1 is 1, so it's 1 dx. And integrating 1 gives you x, and then you plug in 1 and 0, square root. Well, that's already 1. So So your u1 is going to be 1 divided by the norm of 1. That's just 1 itself. Okay. u2 is the second vector, x minus x and 1. You have to do the inner product of x and 1 times times x, no, times 1, sorry. Because that, yeah, I shouldn't be writing this. I should really be saying u1, u1. Okay. And then normal, whatever that is, okay? So when you apply the Gram-Schmidt, it's good to do it in 2 steps. First, compute the projection and subtract. And once you get the vector now, after that, you want to find the norm, okay? So let's do that. What is x u1? Well, that's x and 1, which is integral from 0 to 1 to x times 1 bar dx. And that's going to be just the integral from 0 to 1 of x dx, which is 1/2 x squared. You put 1 and 0, that's 1/2, right? So that tells you that you need x minus x1, 1 is x minus 1/2 times 1, which is x minus 1/2. You still need to normalize this, so your u2 should be this divided by its norm, x minus 1/2 norm is the square root of integral from 0 to 1 of x minus 1/2 times x minus 1/2 conjugate dx. And that's going to give you x squared minus x plus 1/4 integral from 0 to 1 dx, still square root, which is 1/3 x cubed minus 1/2 x squared plus 1/4 x, and you plug 1 and 0, square root is 1/3 minus 1/2 plus 1/4 square root. What's that? That's over 12. That's going to be 4 minus 6 plus 3. Oh, it's it's 1 over square root of 12. Okay. So now you see that since u2 is x minus 1/2 divided by 1 over square root of 12, 4 minus 6, just checking this. Okay. This is going to be square root of 12 times x minus 1/2. Now we still need to do u3, and that's a challenge. u3 is going to be v3 minus v3 u1 minus v3 u2. And in our case, v3 is x squared, so x squared minus x squared and then 1 minus x squared times x minus 1/2, square root of 12 x minus 1/2, square root of 12 x minus 1/2. And if I do x squared 1, that's going to be integral from 0 to 1 of x squared times 1. I'll skip, 1 bar is just 1, so it'll be just this. So it'll be 1/3 x cubed 1 0, which is 1/3. And then x squared square root of 12 x minus 1/2 is going to be square root of 12. They'll go from 0 to 1. See, these are all real, so taking the conjugate is not going to do anything. So let's keep going. And that's going to be square root of 12, 0 to 1, x cubed minus 1/2 x squared dx, which is square root of 12. You get 1/4 x to the 4th minus 1/6 x to the 3rd. And that gives you, this will be 3/12 and 2/12, so 1/12. So it would be square root of 12 times 1/12. And therefore, the numerator of u3, some k2. So some denominator there will be normalizing it, okay? So the numerator part is going to be x squared minus 1/3 times 1 minus square root of 12 times 1/12 times square root of 12, x minus 1/2. But these just become 1. So you end up with x squared minus 1/3 minus x plus 1/2, which is x squared minus x plus 1/6. So that's going to be the numerator for u3, but you still need to normalize it, so let's try that. So k2 that we were talking about is this x squared minus x plus 1/6 by itself, square root, and that's going to be a huge calculation, 0 to 1 of x squared minus x plus 1/6 times itself. Conjugate is not going to do anything because this is all real, so you get square dx. And if you square them, you end up with, if you FOIL that out, you get x to the 4th plus x squared plus 1/36. So these are the squares of each one of these, but then that's not all. You have to multiply pairwise and double them. So this times this gives you negative x cubed, but it's doubled. So it's minus 2x cubed. This times this gives you positive 1/6 x squared, but it's doubled, so it's plus 1/3 x squared. And then this times this gives you minus 1/6 x, and you double it, you get minus 1/3 x dx. And that's 0 to 1. Oh, there's still a square root of x to the 4th plus 1/3 plus 1 is, no, let me do cube first, minus 2x cubed, and then 1 plus 1/3 is 4/3 x squared minus 1/3 x plus 1/36 dx. That gives you 1/5 x to the 5th minus 1/2 x to the 4th plus 4/9 x cubed minus 1/6 x squared plus 1/36 x, and then you plug in 1 and 0. It's still square root. Yeah. And wow, I'm kind of regretting I chose these numbers. Minus 1/2 plus 4/9 minus 1/6 plus 1/36. Well, every one of these can be written as 1/36. No, there's 5 as well. So what is that? That's 180. Okay. So that's going to be 36 minus 90 plus 80 minus 30, and then plus 5. Okay. Minus 10 minus 40. Wow, 1/1. So this is going to be 1 over square root of 180, so that when you divide, you get, so here's the answer. Okay. So you get some horrible answer. If you are following all the calculation, it's going to be 1 stays as 1, but the next guy will be square root of 12 times x minus 1/2. And the last guy will be square root of 180 multiplied by x squared minus x plus 1/6. Okay? So that's an orthonormal basis. Of course, that's a horrible calculation, but it's worth it because once you have an OMB, then trying to figure out a way to express any other vector, it's easy to write down the linear combination of these to make it equal to any other vector. Okay? So the interesting thing about this is that there's some classes of polynomials with different weights that you can use, and they get used in place of Fourier series. So if you're interested in this topic, look for something like Legendre polynomials. And Chebyshev polynomials. And these are Gram-Schmidt applied to different sets of things like this with slightly more modified things. So I'm kind of regretting myself. I should really have done negative 1-to-1, then you can start to see Legendre, and they're cool. So in place of like Fourier series, you can have a series of functions as summation of Legendre polynomials or Chebyshev polynomials. So these are some interesting stuff that you can do.